Hello everyone, I welcome you all to the lecture of Introduction to Physical Metallurgy and Engineering Materials. So in this lecture we are going to discuss about the most important concept, that is iron cementite phase diagram or iron carbon diagram. So basically in this lecture, first of all we will construct the phase diagram, then we will discuss about the major three invariant reaction that is being taking place in iron carbon phase diagram, and we will discuss the most important phase transformation reaction or the invariant reaction, that is eutectoid reaction, later. So let us begin with the construction of the phase diagram. So lots of students try to mug up the phase diagram just to remember what are the invariant reaction and where exactly at what temperature and what composition the invariant reaction is being taking place. But to remember or to basically memorize the iron carbon phase diagram is to understand the concept behind it, that is basically understanding the invariant reaction along with drawing the diagram. So we will do that, but first of all we need to see what is in the x axis. Whenever we are talking about any phase diagram, in the x axis we will have our composition percentage or basically weight percentage of the solute atom. Okay, so as you can see at 0 axis or here, basically we are having Fe, that is representing 0 percentage of carbon, and this is basically the percentage of carbon. Okay, so as we have discussed in other phase diagram, basically the phase diagram go up to 100 percentage of the solute atom, but here the case is different. Here it is limited to this 6.67 percentage of this intermetallic compound, that is Fe3C, which is also known as cementite. So whenever we are talking about iron carbon diagram, so basically we are talking about iron carbon phase diagram. This can also be called as Fe3C, that is iron cementite phase diagram. Understand everyone? Okay. So in the x axis, as I have already told you, that is there will be percentage of carbon, and the percentage is extended up to only 6.67 percentage. And why? Because beyond 6.67 percentage we are not interested about those alloy, because those alloy only possess brittleness because of higher percentage of carbon. Okay, so we are only talking about till this intermetallic compound, that is Fe3C or cementite. As you can see in this Fe3C, that is constitute of 4 atoms, in between which this is carbon is having 1 atom. So 1:4, that means 25 percentage of or atomic percentage of carbon is present in this intermetallic compound. But as the carbon is very lighter in nature, this is only having 6.6 weight percentage in this alloy, or basically the iron carbon alloy, or basically we are talking about steel and cast iron, that we will discuss in the latter part, will be discussed in the latter part. Okay, understood? So in this compound, carbon or compound means that is 3 atoms of iron and 1 atom of carbon. So carbon percentage or atomic percentage will be 25%, but as the carbon is having less weight or lighter in nature, that is why it is only possessing 6.67 weight percentage of this alloy. Okay, now in the y axis we are having all the important temperatures, as you can see, starting with the 1535 degrees Celsius, which is basically the melting point. This is basically the melting point of pure iron. Understood? Okay. Then we are having 1493 degrees Celsius, where your first invariant reaction, that is your peritectic reaction, that takes place. Then this is for 1410 degrees Celsius, which is related to that peritectic reaction. Then there will be 1150 degrees Celsius, or we can say 1147 degrees Celsius also, but because in some books it is written that 1147 degrees Celsius, where the second invariant reaction, that is basically our eutectic reaction, is going to take place. Okay, so basically eutectic point is basically at 4.3 percentage. Basically it is okay. So this is our 4.3 percentage. percentage of carbon. And another salient point that is also required here, because this particular reaction will be represented by a horizontal line, which will start from the composition itself, that is 2.1. Okay, so this is 2.1 percentage of carbon. Okay, so this will be one horizontal line. Okay, and another reaction or invariant reaction, that will be happening at 725 degrees Celsius. So there will be another horizontal line we can draw at 725 degree Celsius. Now starting with the invariant reaction number 1, that is peritectic reaction, which is happening at 1493 degrees Celsius, that is extended from 0.1 percentage of carbon to 0.5 percentage of carbon. Okay, so this is our 0.1 percentage of carbon, this is our 0.5 percentage of carbon, and in between which this is our 0.2 percentage of carbon. So here the phase diagram is something like this. Okay, so from this 0.2 percentage of carbon, one boundary will be extended up to 2.1 percentage of carbon, and from 0.5 percentage of carbon another boundary will be extended up to 4.3 percentage of carbon, and this is another boundary which is extended up to 6.6 percentage of Fe3C. And as you can see, this 6.67 percentage of carbon, or basically the intermetallic compound, is another phase. As it is a compound, it will be considered as another phase, that is having 6.6 percentage of carbon. Okay, so here at 725 degree Celsius, so this is 0.02 percentage of carbon, and here this will be 0.8 percentage of carbon. Okay, so from this 0.8 percentage to 2.1 percentage, there will be another boundary to represent a distinct phase. So we will draw that. Okay, and here the phase diagram will be something like this. Okay, so this completes our the diagram part. Now what we have to do, that we have to represent all the phases that is present in it. Okay, now let me change the ink. So here at the peritectic reaction, so this is our 0.2 percentage of carbon. Okay, so this is basically represented by, sorry, this is not alpha, actually this is represented by beta, sorry, delta. So this is basically our delta iron. So this is our delta iron. Then this will be our gamma austenite. Actually this particular diagram or phase diagram is actually proposed by Robert Austenite, and according to his name, one of the phase is already named, that is, this is our austenite phase. Okay, so we know that this part is completely liquid part, and here at 725 degrees Celsius, as you can see, this part is basically known as your alpha iron or alpha ferrite. This is alpha iron or alpha ferrite. This is delta iron or delta ferrite. Okay, and now we can represent all those combined phases by using 1-to-1 rule. 1-to-1 rule, that means we have to draw one isotherm, basically, which will start from a single phase and which will end at another single phase. So in between two single phases there will be mixture of two phases. Okay, so that means, suppose for example, if I will draw one horizontal line here, or basically isotherm here, so it is starting from the gamma austenite and it is ending at the liquid phase of iron. So this will be your liquid plus gamma. Understood, everyone? So in this manner you do not have to mug up where exactly which particular phase or composition should be named, as we will apply here the isotherm, as this is starting from delta ferrite and ending at liquid. So this will be liquid plus delta. Similarly, here this particular region will be our delta plus gamma. Similarly, as this particular region, or this is the region we are talking about, this is the region, or to know the composition of this region, we will start from here, that is gamma austenite, and the 1-to-1 line will end at the 6.67 Fe3C. I will draw the line. Suppose this is our 1-to-1 line or isotherm I am drawing. So as you can see, the starting point is basically starts from gamma austenite and it is ending at which phase? That is the intermetallic compound cementite. So, what will be this phase? This will be the mixture of gamma plus cementite or gamma plus Fe3C. So, we will write that this will be gamma plus Fe3C. Okay. So, this is gamma plus Fe3C. Similarly, we can name other phases also. So, this will be our alpha plus gamma, and this will be our liquid plus cementite or Fe3C, and this gamma plus Fe3C is named as, or this mixture of the phases will be named as leadovurite. Okay, everyone. So, I guess this finishes your the basic iron carbon phase diagram or Fe3C phase diagram. I actually forgot to mention the uh, invariant reaction. So, let me change the ink. So, this here at 1493 degrees Celsius at 0.2 percentage of carbon, or basically from 0.1 to 0.5 percentage of carbon, the horizontal that we have drawn is basically representing our peritectic reaction. And here the horizontal that is made at 1150 degrees Celsius is basically representing us, and the 4.3 percentage of carbon, it is basically our eutectic reaction. Sorry, this is eutectic reaction, and the third invariant reaction is represented at 725 degree Celsius, that is our eutectoid reaction. Okay. So these are the basic information that we can get whenever we are drawing the iron carbon phase diagram or iron cementite phase diagram. Okay. So, basically this 2.1 percentage of carbon is having another significance, that because basically we know that 0.2 percentage of carbon, we are calling it as the peritectic point. Here 4.3 percentage of carbon, that will be your eutectic point, and this 0.8 percentage of carbon will be representing eutectoid reaction. So, what is basically the significance of this 2.1 percentage of carbon? Basically, it is the boundary between the two major alloy that is being formed under this iron carbon phase diagram. One that is steel, another that is the cast iron. So, basically this part, that is still 2.1 percentage of carbon, that is this part till 2.1 percentage of carbon is known as steel, whereas from 2.1 percentage to 6.67 percentage is basically known as cast iron. Understood, everyone? Okay. So, now let me enlist all the three invariant reactions. So, that will complete the information regarding our iron carbon diagram. So, first, that is peritectic reaction, So, peritectic reaction basically here one solid phase plus one liquid phase upon cooling gives rise to another solid phase, that is gamma. So, here and it is happening at 1493 degrees Celsius. So, here what is the percentage of the delta phase, that is basically 0.1 percentage or 0.1 weight percentage, liquid will be 0.5 percentage and the gamma is having 0.2 weight percentage. Okay. The next reaction, that is eutectic reaction. Eutectic reaction. So, what is happening in eutectic reaction? So, here liquid phase upon cooling gives rise to mixture of two solid phases, that is liquid upon cooling at 1150 degrees Celsius or 1147 degrees Celsius, gamma plus Fe3C, mixture of two different solid phases. Here liquid will be, or liquid is having 4.3 weight percentage. So, gamma will be having 2.1 percentage. As you can see, the horizontal line is extended from 2.1 to your 6.67 percentage. So, the gamma will be having 2.1 percentage and Fe3C is having obviously that is 6.67 percentage, 6.67 weight percentage. That is our eutectic reaction. Next will be our the third invariant reaction, that is eutectoid reaction. Eutectoid reaction. So, what is eutectoid reaction? Here one solid phase upon cooling gives rise to two mixture of two different solid phases, that is gamma upon cooling at 725 degrees Celsius gives rise to alpha plus Fe3C. So, I have actually forgot to mention this one here, that is alpha plus Fe3C, which is also known as perlite. Which is also known as perlite. Okay. So, that is mixture of two phases, that is alpha and Fe3C. Okay. So, here alpha, what about the weight percentage? Alpha is having 0.02 percentage and Fe3C as usual 6.67 percentage and gamma is having 0.8 percentage. Okay. So, these are the three invariant reaction that is being taken. Basically, these takes place whenever we are talking about a complete iron carbon phase diagram. Okay. So, basically some other information I must tell you whenever we are talking about iron carbon phase diagram. Already I have told you that 2.1 percentage of carbon is basically the boundary line between the two major alloys, that is the outcome of this iron carbon phase diagram, that is steel and cast iron. And as you can see in the cast iron part, if you will see at see this horizontal line at above 4.3 percentage of carbon we are having liquid phase. That means for cast iron the melting point is basically 1150 degrees Celsius or 1147 degrees Celsius, which is very less than the pure iron melting point, that is 1535 degrees Celsius. That means at 4.3 carbon percentage, the alloy has the lowest melting point, that is 1150 degrees Celsius. And we already know some idea about the manufacturing technology, that if some material is having lower melting point, that material is best for casting process. That means cast iron can be easily manufactured by casting process. So let me write, that is an important point. At 4.3 percentage of carbon, the alloy has lowest melting point, eleven 150 degrees Celsius, beneficial for casting. Okay. So basically, if we are talking about steel, steel is having much higher melting point as compared to cast iron. So steel has higher melting point, not suitable for casting. Okay. So if we are comparing these three invariant reaction, U-Tector reaction is the most important one, which will be discussed in the next lecture. Okay. So thank you everyone. I hope you have understood the iron carbon phase diagram well, and you do not have to mug up this particular diagram to draw only. Okay. I already told you in the beginning of this lecture that best way to remember iron carbon diagram is to understand all the three invariant reaction. Along with it, you have to draw the diagram so that easily you can mention the binary phases, the combination of those phases. Okay. Uses of 1-to-1 rule. Already we have some basic idea about the phase diagram. Okay. So we have to just apply those rules and we can easily basically construct the iron carbon phase diagram or Fe3C phase diagram. Okay. Thank you everyone.